All right, we were working in section 3.2 last time. We were talking about maximum and minimum values. We had talked through some basic steps to finding some maximum and minimum values. We talked about this idea of relative or local extreme points, being that it's the highest point in a particular area of a graph. And we talked about the fact last time, like we did on your test just now, that just because we have a place where the derivative is 0 doesn't mean we necessarily have a max or a min. It's something that we have to test. And we had gotten through the point where he had done a couple of examples of that, and we were moving on to one other type of extrema, which is where we are right now. Does that sound good? Okay. This type of extrema is called an absolute extrema. Absolute extrema generally is on a specific interval, but it doesn't have to be. I'll give you an example of one that's not here in a minute. But the absolute extrema is actually the absolute biggest or the absolute smallest value for the whole graph. Okay, that's what it is. So if we have a point, C, f of C, it's a location where it is the absolute smallest, in which case it's called the minimum, or the absolute biggest, in which case it's called a maximum. And the extreme value theorem says, we've got another one of these value theorems. We have the intermediate value theorem, the mean value theorem, and we've got the extreme value theorem now. The extreme value theorem says that if you've got a graph where it starts and stops at specific locations, it will for sure have a lowest value and a highest value. So let me draw you a couple pictures. If we were to have a graph that looked like this, I'm not even going to put it on axes because it's not a real big issue. This graph, if it goes up and down forever, obviously does not have an absolute maximum or an absolute minimum value, right? Okay, but what this extreme value theorem is saying is that it's bounded between a specific location where it starts and stops. So again, now let's actually put it on an axis. And let's say that this point is A and this point is B. It means it really does start here and stop here. And those two locations really then would have the absolute maximum, absolute minimum location on the graph. Now, there are some functions that don't need to be bounded to have this. So like consider having a graph of like a parabola. This one has an absolute maximum, but it doesn't have an absolute minimum as drawn, right? There is a location where it is the absolute biggest value on the graph. It's the location that's also a relative maximum. That's what we did last time, right? So we have three possibilities that we have to look at, really two possibilities, that we have to look at when we're finding these absolute extreme points. We have to look at places that have critical values, places where the derivative is 0. We do have to look at that. And then the other thing that we have to look at is we have to look at the end points of a graph if we're on a bounded interval. So we're going to be looking at the bounded interval endpoints and the critical points. And that's what my next slide actually is saying. So we're going to test two types of points. One is relative extrema, the critical points. Remember, this is the place where f prime of x equals 0. And potentially maybe is equal to does not exist in some very rare situations. And then we have to test the endpoints. So if our interval starts at A and ends at B, it means we actually have to test the endpoint at A and the endpoint at B. Now here's something cool. We do not have to do a sign chart for these. It doesn't matter about their local behavior. It only matters about their for sure behavior on the entire graph. So you're not going to see us doing any sign charts on these where we did the increasing and the decreasing, the pluses or minuses, or these straight lines uphill and downhill and things like that. We're really just going to be testing particular points. You guys ready to see an example of this? It's a trig function example. All right, we're going to find the absolute extrema of the given function on the indicated interval. So there's two things we have to test. Somebody tell me one thing we're going to test in this particular function. Critical points. We need to figure out what the critical points are. Let's start with that one since Jen mentioned that one first. So one of our issues is critical points. How do we find critical points? This is a review for what you remember from like 5 days ago. We set the derivative, in this case we've got g, so g prime of x equal to 0. So we actually need to find what g prime of x is. So what in the world is g prime of x for our function? Okay, so Allison says -3 sine of x. Do you guys agree? Yep. Awesome. So then what are we going to do, Sam? What's the next thing? Got the derivative. What are we going to do with it? We will plug a number in later, but not into the derivative. We are going to do some of that. We need something to figure out. I mean, what are we going to plug in? How are we going to find that? We're going to do it equal to 0, and then we'll have the numbers to plug in. So we are going to get to the point you're mentioning, just not quite there yet. We need to figure out where this is equal to 0. Okay, so here's the question of the day for you. Does the -3 affect where this thing is equal to 0? It really doesn't, right? So we can either think of dividing by the -3 or just ignoring the -3. But this question boils down to, where does sine of x equal to 0? How do I solve that? What'd you think of, Mackenzie? The circle, yeah, that unit circle. You guys, I know you think like that this is like the biggest deal. It is so helpful. That unit circle is amazing. All right, so think unit circle for me for a minute. Or you can think of the graph of sine, if that's a more visual image for you to connect to. I need to know, where in the world is the sine graph equal to 0? Or where on the unit circle is sine equal to 0? It's going to be pi values. So think about pies, right? Half pies and whole pies and quarter pies and things like that. It's all about pi on the unit circle, remember? Okay, so we think maybe pi over 2. That one doesn't work. You think it's 0 and pi? Does anybody else think that that looks right? It's actually all of the whole pi values. So 0 and pi and 2 pi and 3 pi and all the negatives as well. I mean, so we could even do like -2 pi if we needed it, or -52 pi if we needed it. I mean, any of those things. I mean, any positive or negative whole pi values. I mean, that's what we're looking at. No fractions, in other words. Okay? And as we're taking a look then, what do we care about? I mean, like, this is a lot of values. I don't want them all.
Between those two.
Right. Up here at the front, we were given an interval. I really only care about the values on that interval. Are any of the values that I listed on that interval? Pi is. It's the only one, isn't it? That is the only whole pi value between pi over 2 and 5 pi over 4. Half of a pi and a 1.25 of a pi. There's a whole pi, just one whole pi in between. So this right here is my critical value. This is the only one I get. So critical number or critical value. All right, so that's one thing I'm going to test. Now I know what my critical value is. What's the other thing that I have to test? There's one other thing on that page, the page before this one. And it was the slide before this one as well. Endpoints. Okay, what are my endpoints here? It's not a trick question, I promise. Yeah. Yeah, it's just the interval, the pi over 2 and the 5 pi over 4. All right, so I mentioned this because what I want you to see is that you only have 3 points to test, right? 1, 2, and 3. There are only 3 places that this graph can have an absolute max or an absolute min value. There's only 3 of them. Because I'm confined to a very specific little window, right? It's like taking your calculator screen and setting your calculator screen at negative pi over 2 for the max, the minimum value, and positive 5 pi, I'm sorry, I said it wrong. Positive pi over 2 for the minimum value, and then 5 pi over 2 over 4 for the maximum value. I've only got this tiny little window I'm looking in. All right, so I need to figure out which of those 3 is the maximum, which is the minimum, and there's going to be one of each. That's what the extreme value theorem said. It says I have to have one of each. And I might actually have more than one each. That's a possibility. So what do? Well, all I have to do is to test those values in the original function. Oh, the original function's name was g, wasn't it? I will use g to be precise. So we're going to test g of pi over 2, and g of 5 pi over 4. And honestly, I know that these are unit circle values, but it's totally fine for us to get decimal approximations to compare them with, because that very well, I mean, like comparing square root of 3 over 2 to square root of 2 over 2 is not clean. It's doable. You guys can think through it, but it's a little bit cleaner to look at the decimals. So it's appropriate to think about it that way if that's helpful to you. So we're going to do, it was cosine, right? 3 cosine of pi, 3 cosine of pi halves, and 3 cosine of 5 pi over 4. And some of these are approximations, some of them are exact. What do you get for the first one? What is 3 cosine of pi?
1, 3.
Oh, you've given me 3 answers, Allison. Negative 3? I don't even think that's one you said, was it? That's okay. They were all values from the unit circle you were using, so that part's good. It is negative 3. So everybody agree with that? Okay, good. What about 3 cosine of pi over 2?
0.
That one's 0. And how about 3 cosine of 5 pi over 4? And let's just go with a decimal. Negative 2.12. Okay, sounds good. So this one's actually an approximation. Looking at the 3 values, which one is the biggest? Yeah, this is the biggest value. So this is where I've got my maximum. I'll write it out in a minute differently than this, but that is my biggest value. What is my smallest? It's negative 3. Okay, so the question says to find all absolute extrema on the indicated interval. So we're going to write down what we found. We found that we have an absolute, we'll start with maximum, of what value? What is the maximum value? 0. 0 is the value at x equals what? What was the x value? That's the pi over 2. So this tells us both the maximum value and it tells us the location where the maximum value occurs. And we're going to do the same thing for the minimum. The absolute minimum of what? Negative 3, right. At x equals pi. And that's the answer that we have come up with using this process. Absolute extrema, we test 2 types of points. Critical points and endpoints. And there's no need for a sign chart, right? Because at the end, we actually test those points specifically, which is a little different. All right, one more question in this section, and then we'll be finished with this one. This is one of those questions where your graph and my graph might not necessarily look the same, right? But they could both be correct. It says sketch a graph of a function with the following characteristics. The function has an absolute maximum of 3 on the interval negative 2 to 2, and the absolute minimum does not exist. Now notice it didn't say does not exist on the interval negative 2 to 2, right? In fact, it can't say that, right? Because the extreme value theorem says it has to exist on that interval. It just says it doesn't exist in general. So be real careful with the language that you're seeing on these and what they mean. All right, so we're going to draw a graph. On our graph, we do need to have the negative 2 and 2 marked to give us some perspective of where the graph is going to have a maximum. I think it said maximum, yeah. And what was the maximum value it has to have? 3. So somewhere in between there, we actually have to hit the x value of 3, and we can't go above it. Okay? So try something real quick. See if you can sketch a graph that has an absolute maximum of 3. That maximum occurs between negative 2 and 2. But the whole graph as a whole does not have an absolute minimum. Just try something. If it doesn't work out, you can always put a big old X over it and draw it again. You got some space there. general shape you guys drew? An upside down parabola? Did anyone else draw an upside down parabola? That's a good thing to draw here. It fits really well. Did everybody actually cross the x, or hit the height of 3 on the y-axis? Did everybody do that? Do you have to do that? You wouldn't have to. It kind of feels natural because of the way that the graph was described, but you certainly could have hit the maximum somewhere else. For example, maybe your graph looks like this, right? Maybe it doesn't even look like a parabola. Does it have to look like a parabola? What else could you draw? Squigglies, so something that we did like this. You could, yeah. Any other graph? And I would do it on the other side as well. Anything else you can think of? There's another graph that you've probably seen before that you could draw. A graph that looks like this. Yeah, you could. That's a very good example. You could also draw something that looks like this. Do you remember what that graph's called? Absolute value graph. So there are choices here. That's just my point, is that there are some different places. But most of you were inclined towards that parabola probably because I had shown you a graph of something similar to that earlier.